All right, this table attempts to explain or provide an overview of the interconversions between carboxylic acids and derivatives, also between derivatives. And most of these reactions occur by nucleophilic acyl substitution, not all of them, but nearly all of them. And the way the table is set up, starting with is on the left side of the table, much as the reactant would be on the left side of a reaction arrow, and then what you're making is to the right of that. And in both cases, they're organized from most to least reactive, most to least reactive. And a general rule is that you can go from something that's more to less reactive, and there are a few exceptions to that. You cannot go from a less to a more reactive. So exceptions to this, you can go from a more to a less, you can only go from more to less reactive, except you cannot go from an acid, carboxylic acid, to an amide, because what happens there is you get a proton transfer instead. And then you cannot go from less to more reactive, except you can convert anything into a carboxylic acid, because carboxylic acids are defined based on their ability to go to a carboxylic acid. And you can take a carboxylic acid and make most, but not all of the derivatives. And both the Klein text and the UCI lectures do a very good job of explaining the thermodynamics, complete with reaction coordinate diagrams, of why you can go from more to less and not less to more reactive. But, in general, even with acid-base chemistry, you're always trying to go towards more neutral, less reactive. So since the acid chloride is the most reactive, we can make the most things out of it, is one thing to notice. And so as we progress down the table, we can make fewer and fewer things. But again, notice we can take any of these and convert them into a carboxylic acid. And likewise, we can take a carboxylic acid and convert it into most things, except not into amides, because you get a proton transfer instead. The empty boxes that I put the slashes across are for a functional group going to the same functional group, which generally is pointless. An exception to that is the esters, and we'll talk about that when we get to the esters. So I'm just going to do kind of a quick overview here, and as you're reading the book, you might want to have this chart out and keep checking off what you're learning. So starting from acid chlorides, you can react these with a carboxylic acid to make an anhydride, an alcohol to make an ester, or water to make a carboxylic acid. And in all of these cases as written, it shows pyridine as a reagent. And remember that pyridine I'll stick it off to the side here. So pyridine is a 6-membered ring aromatic tertiary amine, and as such it is a good base. But tertiary amines are not effective nucleophiles. And so the role of the pyridine in all of these cases is to neutralize the HCl that's formed from the chloride and the hydrogen. You can also do all three of these reactions by using the conjugate bases of these reagents, and then you wouldn't need to use pyridine. You can also make an amide by reacting, so this is a primary amide, so we use ammonia. To make a secondary amide, you would use a primary amine. To make a tertiary amide, you would use a secondary amine. And the role of the excess nitrogen is that the second equivalent neutralizes the acid that's formed. And so if you have ammonia or you have an amine that's not particularly valuable, that you don't care about, you can just use it sacrificially and one equivalent makes the amide and the other equivalent gets neutralized. If you have an amine that you care about, then you might use a different base. You might use, for example, you might have pyridine in there that won't react as a nucleophile. We do a lab like this in Chem 24, and there we actually add sodium hydroxide dropwise during the reaction so that the pH never gets too low. So again, from an acid chloride, we can make anything. The reactions of the anhydrides, both the nucleophilic acyl substitution and the other ones that we learn in this chapter, are very similar to the acid chloride reactions. And in fact, the section on this in the book is, in the Klein text, is really, really short because basically he says they do all the same things that the acid chlorides do. Except that we don't need pyridine, and the reason that we don't need pyridine is that instead of generating a strong acid, we generate a weak acid from the acetate. With the amide, you have to be a little more careful here just because amines and ammonia are bases, and if the solution gets too acidic, you won't have a nucleophile anymore. But here we still need the excess NH3 because NH3 and acetic acid will react. So esters, we can hydrolyze to carboxylic acids, and we can do that either in acid or in base. So we're now entering the realm of the less reactive carboxylic acid derivatives, and they need help. So either help in the form of an acid to protonate the carbonyl oxygen and make the carbonyl more reactive, or help in the form of doing the reaction in base, and where you bake a better nucleophile. Because remember, any reaction, you have a balance between the two reactants. If you have two things that are really reactive, something's going to happen, maybe too much. If you have one thing that's reactive and another one that's not particularly reactive, you might still get a reaction. But if you have two things that aren't particularly reactive, then probably nothing's going to happen. So if you think about, two people that are partners or roommates, and in an era where we're actually allowed to go someplace, if both of those people really like, to go out to eat, they're going to go out to eat a lot. If one of them really likes to go out to eat and the other one really likes to stay home and cook, well, they're not going to go out to eat as quickly, but, they're still going to go out to eat some of the time. However, if you have two people that would both rather stay home, they're never going to leave the house. So that's kind of your analogy for that. So esters and on down are going to need some sort of a help. The base reaction is referred to as saponification, which refers to the fact that it's the way of making soap. And I think I did an example of that someplace else. And then you can, in theory, turn esters into amides, but this reference means that it's not useful, which in chemistry parlance means it's useless. Or not practical is another nice way to say that it's useless. So this is typically not done. The transesterification, which they mentioned in the UCI video, but I don't believe is in the Klein book, would be a way of converting one ester into another ester. And that's a real thing, and I think it also appears in some biochemical pathways. So there's esters. Yeah, that's it. Okay. So carboxylic acids we can turn into anything. So we can react them with thionyl chloride, much in the way we reacted alcohols with thionyl chloride. Part 1 of the mechanism converts the OH into a better leaving group. Part 2 of the mechanism actually is a nucleophilic acyl substitution. We can react them with acyl halides to make anhydrides. We can react carboxylic acids with alcohols in the presence of an acid catalyst. And this is a Fischer esterification, which is a lab that we do in Chem 24. A pretty classic reaction. We can't do this reaction in base. And the reason we can't do this reaction in base is that the base would pull off the proton and then that's the end of it. And in a similar vein, if we react a carboxylic acid with an amine, all that happens is you get a proton transfer. So sometimes when you combine a weak acid and a weak base, you get a reaction that doesn't happen, and sometimes you get one that kind of happens, and sometimes you get one that's pretty efficient, and this one is efficient enough. So the reaction that's efficient enough is the proton transfer, meaning that we're not going to make an amide by taking a carboxylic acid and an amine. And then for amides, so we can take amides, and in theory, you can take an amide and you can convert it into an ester. So my note here is that this is technically possible, but it's difficult and needs what the UCI lecture refers to as special reagents, meaning it's really hard. We can take an amide and with difficulty, either in acid or in base, hydrolyze it to a carboxylic acid. It's a good thing for us that amides are relatively unreactive, because amides are what the bonds in peptides and proteins are, and if it were easy to hydrolyze those, we'd probably all turn to little puddles of mush. Amide to amide, no. You can take an amide and convert it into a nitrile using thionyl chloride, and you're just using that as a dehydration reaction. And by the way, that is a mechanism for which you are not responsible. Another mechanism for which you are not responsible is this one. And then finally, the poor nitrile, you can't do a whole lot with it, but you can take it and hydrolyze it to a carboxylic acid, again with a fair amount of difficulty. What happens is you hydrolyze it to the amide, and then the amide gets hydrolyzed to the carboxylic acid. You don't need to know the mechanism for the conversion of the nitrile to the amide, but you do need to know the mechanism for the amide to the carboxylic acid.